That brings me now to the last problem, which is problem 5, which is 3042, my last problem. A little bit of a mathematical problem perhaps. I have a current I here, and I have here a loop, and the loop has length L. This distance is little a, this distance is little b, and I have a changing current di dt. Well, first of all, the current I will produce a magnetic field pointing everywhere on this side in the paper and everywhere on this side out of the paper, but we're only concerned on this side. The di dt will make the current grow, and so I, as a function of time, equals some I0 at time equals 0 plus di dt times t. It's growing linearly. Lenz's law, Faraday's law says I don't like that. I don't like this magnetic field in the paper to grow. I don't like the magnetic flux through this surface to grow. And so what does it do? It creates a B induced in this direction. How can you get a B induced in this direction? That's only possible if you have an I induced in this loop in this direction. Therefore, electric fields in the wires that contain resistance in this direction. Now, how are you going to go about it? The growing magnetic field will give a growing flux through this surface, and that gives you then a counterclockwise induced current. To calculate the change of the magnetic flux, we have the closed loop integral of E dot dl. I'm only worried about magnetic flux, about absolute values. I don't care about minus signs. That is d dt times the integral of B dot dA over that open surface. And now what I have to do to calculate this properly, I have to take a slice out of here. I take a slice out of here at distance r, and the width of the slice is dr. And the magnetic field at that position r, away from this wire, which current I, is something that you by now know by heart, is mu 0 I divided by 2 pi r. So the magnetic flux, the teeny weeny little magnetic flux going through this small narrow ribbon, of which dr, that d phi r, this is the magnetic flux at location r, is the magnetic field, times this surface area, since this was L, which is L dr. And so, if I do an integral of the magnetic flux, then I have to do an integral all the way from A to B of that magnetic field, L dr. This is the surface area. I integrate r from A to B, and what do I find? Mu 0 times I times L divided by 2 pi times the logarithm of B over A. Because remember, BR is inversely proportional to R. I think we're done, because all you now have to do, and you're perfectly capable of doing that yourself, you now have to take the time derivative of phi, that gives you the phi dt, and once you know the phi dt, you know the integral E dot dl, and you can calculate the induced current. So it's simply a matter now of taking the time derivative of this one, and what you're going to see is that what is very important is the magnitude of the IDT. The larger the IDT, the larger the induced EMF in the system.